commonly a tugboat, is an assistance boat which helps in the mooring or berthing operation of a ship by either towing or pushing a vessel towards the port. A harbor tug in the Caribbean has between 600 and 3,500 horsepower engines, that's 500 to 2,500 kilowatts, and a power-to-tonnage ratio ranging between 4 and 9.5 for harbor tugs. This is an incredibly high ratio, especially considering the ratio of cargo ships or vessels varies between 0.35 and 1.2. Conventional tugs are the tugs we have been using since the start. They are made using the oldest known principle of tug development. The conventional tug has less maneuvering capability but is still used in almost all ports worldwide. With technological advancements, tugs are fitted with diesel engines with either one or more propellers. Single propeller tugs are classified into right-handed conventional and left-handed conventional tugs. Right-handed conventional tugs are more common and likely to be used than left-handed ones. These are highly reliable. The essential components of conventional tugs are as follows. They have a classic rudder. They often have a towing hook provided in the center of the tug. Along with other components of tug positioning, a hook is of enormous importance. The safety and performance of the tugboat mainly depend on the towing point location. The propulsion unit is at the stern. In the conventional tugboat, the propelling device is generally diesel-driven. The propeller develops thrust in water and is responsible for ship's movement. These tugboats are designated based on several propellers in them. Single-screw tug implies one conventional propeller tug, twin-screw tug implies a two-propeller traditional tug, and a triple-screw tug implies three classic propeller tugs. In conventional screw propeller tugs, a movable nozzle and rudders are provided, but the whole propeller is immovable or fixed. The main advantages of conventional tugboats are as follows. The construction of these tugs is simple and requires less maintenance, so the maintenance and construction costs of these tugs are comparatively low. They assist with pushing and tugging operations while carrying towing on a line. The operation cost is relatively low and economical while working with moderate-sized vessels. There may be certain disadvantages of conventional tugboats, and these are: the old design degrades performance standards. They are unidirectional and cannot work in the reverse direction until provided with a reduction gear to facilitate reverse flow. There is more chance of propeller cavitation with these tugs. These tugs have less stability and strength than the modern designs. The repositioning of the tugs is relatively slow due to the limited maneuvering capacity. There is more chance of capsizing or overturning the vessel, which results in fatal accidents. A release hook is required to overpower this issue of capsizing and halting the development of girding. Conventional tugs have low power going astern. Tractor tugs use a multidirectional propulsion unit, similar to a large rotating outboard motors. The tug's thruster units are more or less under the bridge, facilitating spectacular maneuverability in the right hands. The towing point can be placed much nearer the stern to get maximum output from the propulsion units, and therefore, the thrust is always outside of the towing point, thus creating an effective turning moment. Some of the advantages of tractor tugs are: they provide full thrust over 360 degrees. They have rapid power on response time and are well known for their outstanding maneuverability. In contrast to conventional tugs, tractor tugs are adaptable to repositioning swiftly at the pilot's will or on demand of the towing job in which they are employed. Thus, they are readily available tugs with high efficiency values. Their straightforward control systems pose a low risk of girthing or capsizing. These have extraordinary performance and fast speed. They can effectively overcome the forces of interaction with ships at close distances. They can work efficiently in sideways movement due to the close location of the propulsion unit to the turning point. They have improved operational capability in restricted areas. And they have reliable and robust propulsion units. Tractor tugs are complex and costly. They are considered to have very high capital investment costs. The initial cost of tractor tugs is very high. The repair and maintenance of complex underwater units of these tugs are expensive. Other drawbacks are, they have less bollard pull than ASD tugs. Handling in an open seaway might be poor. The underwater units may be damaged on grounding. Their draft may be up to 5 meters, which is significant in comparison to conventional tugs. The retraining of conventional tug masters is essential to maximize a tug's potential. With stern drive, or ASD, tugs are midway between conventional and tractor tugs as these utilize some of the benefits of both traditional and tractor pulls. It can have 2 towing locations, one forward and one amidship, and the main propulsion is from 2 rotating azimuth units, which are placed like a traditional twin-screw tug. ASD tugs are considered more efficient than conventional tugs, but less efficient than tractors. The significant advantages of using ASD tugs are, better directional stability at speed. They have a more suitable hull form for open waters and working in a seaway. They have increased bollard pull. The azimuth units are easy to withdraw for maintenance and repair. And they have a shallower average draft of 3 meters. ASD tugs are challenging to work with as compared to tractor tugs. Some of the drawbacks of working with these tugs are, the sidestepping ability of ASD tugs is not so good. The squat at the stern and flooding of the aft deck have been acquainted with certain types when backing with full power. They are still susceptible to girding or capsizing when using the aft towing position. It is not uncommon for 99% of all towing on ASD tugs to be limited to a forward position. These types of tugs are slightly more at risk from the interaction effects. They have somewhat complex control systems. These tugs are more susceptible to rubbish damage in propellers. Bollard pull is a measurement used to determine the pulling power of a vessel. It is exceptionally important for tugboats. A technical definition of bollard pull would be the thrust developed by a vessel's propulsion systems at 0 ahead speed. There are 2 types of bollard pull, static bollard pull and continuous bollard pull. The static bollard pull is measured shortly after the start of the test, when full power is possible thanks to the still water. The continuous bollard pull is then measured over 10 minutes. The bollard pull of tugs is calculated in kilonewtons or occasionally in different units of force like tons. The average medium-sized tugboat has approximately 500 to 600 kilonewtons of bollard. Every vessel that is required to pull a load must have a bollard pull certificate from one of the classification societies. To calculate the bollard pull of a vessel, the vessel is anchored to a pier using a bollard. The vessel then propels itself forward at maximum thrust, and the tension measured in the towline shows the total thrust achieved. The bollard pull test can't be carried out in all conditions. Instead, a few criteria must be present for the bollard pull test to be accurate. The most important are, undisturbed water, enough clearance around the vessel, deep water, and an unhindered propeller wake and stream. It should be remembered that perfect conditions are rarely found. Therefore, the results of the test must have some margin of error. The tug's power and maneuverability directly affect the tug's price and usefulness. The main types of propulsion units are conventional, azimuth stern drive and tractor. The location and characteristics of the propulsion units are an essential input into all maneuvering decisions. Awareness of the propulsion point is an essential component of deciding how to execute the pilot's commands. The propulsion point is the focal point of the tug's application of horsepower underwater. And it depends on the location and type of propulsion. Azimuth thruster is a type of marine propulsion system that consists of propellers mounted in pods, which can rotate 360 degrees around a vertical axis. This design allows for enhanced maneuverability of vessels, making traditional rudders unnecessary. Azimuth thrusters are particularly beneficial in applications where precise control and agility are required, such as in tugboats. The azimuth stern drive is a specific application of azimuth thrusters where the propulsion units are positioned near the stern of the vessel. This configuration allows for exceptional maneuverability, enabling the vessel to move in any direction with precision. ASD tugs are commonly used in harbor operations and offshore support roles. Many conventional tugs use nozzles around the propellers, with the rudder aft of the nozzles. Nozzles are necessary when a maximum thrust is required at low hull speed. The tug is a good example, as well as a fishing trawler. Whilst fishing at low speed, they need nozzles. Nozzles can be in a fixed position with a rudder placed on their aft part. Towing winches and towing lines are both expensive to start with, and then there are maintenance costs. In smaller ports that are visited by smaller ships not so frequently, tugs equipped with towing hooks may use the lines of the assisted vessel. In this case, it is extremely important to use a line of sufficient strength and in good condition. Always inspect the lines externally and internally, if they are to be used for tug assistance. The staple functions as the tug's towing point and is subject to extraordinary strain. The staple is the primary focal point of the tug's bollard pull when on the towline. The staple itself must be heavily constructed and mounted in such a manner that connects it to the tug's internal frames. The towing point is the last physical point on the tug that fairleads its line, or the contact point between tug and ship when the tug is pushing. The winch fitted on a tug will depend on the towing line to be used. The diameter and length of the towing lines used will depend on the size of the ships being handled and dictate the size of winch required. Wire rope and the more expensive synthetic ropes have smaller diameters per ton of safe working load, while regular-priced synthetic rope can be quite thick for the same safe working load. It is recommended that the towing winch brakes should have an appropriate static holding capacity to that of the documented minimum braking load of the largest towline to be used. The holding capability should be calculated for the outermost towline layer on the winch drum at which towing will be performed. The design and scantling of the towing winch, especially its supports, should be capable of withstanding the braking load of the main towing wire rope without permanent deformation. It should be possible to release the tension on the winch drum in an emergency, and in all operational modes. The end attachment of the towing wire rope to the winch drum should be of limited strength, thus forming a weak link in case the towline has to be run out. After an emergency release, the winch brakes should revert to normal function without delay. It should also be possible to carry out the emergency release sequence, emergency release followed by application of brakes, even during a blackout. Rubber fenders provide cushioning that absorbs impact energy, protecting the vessels from potential damage during docking and maneuvering. By minimizing the risk of damage to both the tug and the vessel it is assisting, rubber fenders contribute to cost savings over time. The expenses associated with repairs, maintenance, and insurance claims can be drastically reduced when effective fenders are in place. With the assurance that rubber fenders will protect against potential collisions, tug operators can focus on executing their tasks efficiently. This increased operational efficiency translates into improved service delivery and better overall performance in marine operations. Regular inspections and maintenance are crucial for ensuring the longevity of rubber fenders. This may involve checking for signs of wear and tear, cleaning the fenders to prevent debris accumulation, and replacing any damaged components promptly. Cylindrical rubber fenders are commonly used due to their versatility and effectiveness in absorbing impacts from various angles. They are ideal for tugs operating in busy ports where space is limited. Tires are not fenders. They are not intended to be used as them, and are not particularly suitable for the task. The main reason they are used is that they are cheap compared to any decent foam, fixed rubber, or pneumatic fender. The only reasons to use them on pneumatic fenders is to protect the fender skin and/or to increase standoff at low cost.